Okay, so thank you for joining, and we're going to cover today super meshes. And super meshes, hopefully you've had some experience with it. If not, don't worry, I'm going to go over everything step by step. And the idea is that hopefully by after today's video, you should feel way more comfortable and ready to tackle any type of problem involving super mesh. And again, what is super mesh? It's essentially mesh, but a special case. What we're going to look at today is just really two options when you're looking at current sources within a mesh type of problem. So let's just go ahead and get started. So if you see here, I'm going to go through 4 different examples. And when you look at these problems carefully, there's 2 rows here. The first row again is covering what is a current source that's not shared among the circuit. So how do we tell that? Well, if we look at this current source, for example, over here, the current's only on this branch. So if you know that it has a value, say it's 10 amps, that 10 amps is only going to start from this bottom node, which is the ground node, back up to the top, and then go to the other 2 branches as well. Similarly, if you look at here on the right, you notice that this is on its own individual branch. There's nothing else influencing that current source. Same with the one on the right. It's just a current source. If it's 15 amps, it's 15 amps pointing in the downwards direction. And if you look at what's different, so look at the bottom 2 images over here, those are actually current sources. So they're on this branch, but there's influence between this loop over here, right? And there's also going to be influence from this loop over here. Well, how can you tell that right off the bat? Well, if you can imagine that this is not a current source, it's just a resistor. That resistor, as you learned from the prior video, is that it's going to have an impact within this loop and that loop as well. And same with this circuit on the right. As you can tell here, if I, for a brief moment, replace that current source with resistor, you'll recall that they'll be the same as being shared with an influence of the current on this loop, and also contribution from the current that's actually happening on the right loop as well. So the top 2 problems over here hopefully will be relatively easy for us to solve. The 2 ones here, more of the classic super mesh type of problems that we have to go into details we can learn how to master in a moment. So let's go ahead and take a look. So if we look at this example, now we're going to actually apply some numbers to that. So we have a circuit here, which is essentially 2 loops. And we also will detect that this has 2 nodes. It has our ground node, which takes across this entire base over here, and this top node here, which is shared with these 3 branches. Okay, so I put in purple the 5 amp source because again, we're tackling now how do you do mesh with current sources. So if you do have that, well, we're going to do what we've done before with mesh, is that we're going to try to apply Kirchoff's voltage law, which means that you sum up all the voltages in a loop, and this should equal 0. So if we look at that, and we now recall from our steps, the idea is that I will, 99% of the time, going to go clockwise. I'm going to first go clockwise for all loops in my problem. Secondly, I'm going to give it a name. So I'm going to call this one I1 and I2. I'm going to label it, which is my current, and my mesh current is what it's actually called. And then I'm going to try to write its equations. Again, see, clockwise direction. For mesh, we're going to do, for currents entering a resistor, we're going to assign it a positive sign, which is really important. There's really a voltage drop across those resistors. We're always assuming the direction is going to be clockwise, and we're going to do the writing our KVL for each of these loops. So those are our simple steps. So again, if we follow that, as I mentioned before, so the currents entering a resistor is going clockwise. We're going to assign it a positive as it enters, a positive as it enters this side. Then it goes back to the ground or the negative side of 20 volts. And same here, so if I start at this corner and I go clockwise, it's going to enter into the 6 ohm resistor as positive, enter into 3 ohms as being positive, and back around. Okay? So remember, Kirchoff's voltage law is voltage, which is really important. So we're going to try to look at each loop. So let's go ahead and start with the left loop. I like to always start with my left loop. And when I start up my left loop, let me do a copy and paste to see if that brings everything down a little bit more clearly so you can see it as I talk about it. So if I look at this in detail, I did that over here already, which is great. You'll notice, let me put it here for you. Shrink that down. So what you'll notice is that if I start here on the left hand side, I always start in the bottom left hand corner. I read what I first see for each component. So I'm entering into the negative 20 volts. So I put here negative 20 volts. Then I go clockwise and I go into the positive end. So I get positive, right? Positive 4 times, and I'm in loop 1, I1. So it's 4 times I1. Then when I get to the positive, I'm entering the positive 6 ohms. Because I'm in loop I1, it is countering loop I2. It's going to be 6 times by I1 minus I2. And again, I went over this in detail in previous videos. And then what's really important for us is that each one of these, right? Each one of these parts here, this is a voltage. A resistance of 4 ohms times by a current gives me back a voltage. A 6 ohm resistor times by a current gives me back a voltage. So I have a V term here, a V term here, and a V term here is really important. So now if I repeat that and look at loop, the second loop on the right, and I did the same exact thing, and I started off on this corner. I'm going to have here positive 6, but I'm in loop 2 now. So I'm I2, so I'm going to have I2 minus I1, because if I'm in loop number 2, it appears as if I1 is going counter my direction. So I'm going to have 6 times by I2 minus I1. So here I have a resistor times by a current, gives me voltage. Then I get to the 3 ohm resistor. Then I have a 3 ohms times it by I2, right? Because I'm in loop 2. And then I have something weird here. I put it in red. So what do I do with this? So again, what am I trying to say? Is that this is here a voltage term. This here is a voltage term. What? You know, this is not a voltage term, right? So something's not right. So it turns out is because in this condition where you have a current that's in a branch isolated among itself, the current is what it is. So what does that mean? So an important takeaway here is that we actually didn't have to do anything to loop 2, right? Loop 2 was actually unnecessary to actually do. What's important, so I'll say it slowly, I'll cross this out for a moment. So what's important is that because in the second loop here, loop number 2, there already is a current source here that's 5 amps, and that 5 amps is isolated to this loop, then the current is 5 amps throughout. So it's 5 amps from this bottom node, goes up, and it's 5 amps all the way through the 3 ohms. And as it reaches this node, it stops right there. This is extremely important that you understand why. The second thing is that it's minus 5 amps. Why? Because again, I'm assuming my direction to be positive, always clockwise. I'll put it here, I'll write it out. So again, so here's my drawing. So anytime I go clockwise, my clockwise is going to be assigned the positive value. I'm going to put here CLK, which means clockwise for me. So if I assign that to be clockwise, and I'm looking at this problem, and as I go clockwise, if 5 amps is opposing my perceived direction of going clockwise, then I'm reading that 5 amps as not being positive. It'd be positive if the arrow's facing down because it's going upwards. It's actually read as minus 5 amps. It's really, really important. So what does this mean again? So whenever time you have current in one branch of a circuit, and it's isolated to that only one branch, no other way for it to, it's not shared among any other branches at all, well, I can define that current with whatever's given. So hopefully this makes sense. This is 100% will be 5 amps here, 100% will be 5 amps here, will be 5 amps here, 5 amps here. The entire branch itself is all experiencing 5 amps. So which means that for a problem that has one current source isolated, it's really an easy problem. You only have to write one equation. That one equation that you need for this 2 branch, sorry, because this is 2 branches only. So I only need I already know half my problem. I know I2. So because I know I2, I can literally substitute I2 into this equation. I only have one unknown, which would be my I1 value. And if you're wondering, well, how do we get the current across the 6 ohm branch? Well, we figured out before that the current I1 minus I2 will give us that current as well. So let's take a look at this. So I showed you the work over here. So because of that, I'm going to plug in our value of the minus 5 amps. So minus 5, 6 times it by negative, sorry, let me write it out over here. So I think I want to make sure I'm clear. So it's going to be 6 times it by I1 minus a minus 5 amps, right? And remember, this is 6 ohms, so it'll be a little bit more clear for a moment. So that's going to create this voltage value. You multiply these two, right? So I get back this 30 volts over here. Now back to 6 I1 when I distribute this out, 4 I1 and minus 20 volts, okay? And when I simplify this, I can finally get the current to be -1 amps. That is on I1. So what does the -1 mean? There's no such thing as negative current. It just means my direction is going opposite direction that I assumed it to be. I assumed that I1 is going to be clockwise, but it turns out that based on the math, that is actually going the opposite way. That's all it is. It's still at 1 amp, but it is 1 amp going counterclockwise is how you should be interpreting this problem as. Okay, that's really important. And I'll get back to you to show you if you want to know a little bit more detail on how to solve for the 6 ohm, but again, it'll just simply be the -1 amp minus the 5 amps will give us the current going through the 6 ohm resistor. And I'll show you that when we get to more challenging problems later and how to approach that, and hopefully it becomes second nature. So if we look at this problem over here, and this is our second example problem, this time, right, we have here 2 currents sources and 3 loops. So I have a 6 amps on the left, I have an 8 amps going on the right. This one's going down, this one's going up. So the question I have for you is, how many nodes do we have? We have 1, 2, 3, 4, 5 nodes, right? So take a moment to think about that. Okay. So when you look at this problem, what you should hopefully see is that there's a ground node here where they all share the same node, which is called our reference node or our ground node, which would they all be attached to. And on the top, there's one node over here and another node over here. So if you include the ground, it is 3 total nodes for this particular problem. All right, so take a look at that. So what I want you to, the next steps to recall is that then you have to label each of those mesh loops, and you also have to define or give a name to the mesh currents. I'm calling it I1, I2, and I3. And again, as I mentioned before, I'm going clockwise always, at least 98 to 99% of the time. So I identified that to be my clockwise direction. And remember what I said before, because 6 amps is by itself, so there's no other portion of the circuit that's being influenced, and I'm going to have 6 amps from here all the way here. I have positive 6 amps, because notice the current is going the same direction clockwise. And same here, so if I start here in this corner, I go clockwise, my I3 goes down, so that means I'm going to be positive direction for the 8 amps as well. Let's take a look at that. It's pretty important. So let me say it one more time. So I always start in the bottom left-hand corner. I go up, right? And it's going the same clockwise direction. If I continue this cycle, that means I have a positive 6 amps. If I start on this corner and I go in a loop, you'll notice I'm going in the same direction as this arrow, and I continuously going. So that means this arrow is also going the clockwise direction. Okay. So I drew this in another way as well to help you out the visual about this nodes and trying to understand what's actually happening. But here's a different variation of the drawing. Remember that these wires are not really rigid and square and always going to be rectangular form. They're kind of, you can think of them as also being flexible if that helps you imagine this a little bit more clearly. So in this variation of the drawing, you can see that how the branch looks like with the 6 amps. So it's probably hopefully a little more obvious that the 6 amps is definitely isolated here, right? And so is the 8 amps will be definitely isolated here. No contribution from this branch. And I'll show you the other. And here's a more advanced, or at least how I like to imagine it. So in my mind, this is how I perceive this problem. Is that, again, this is all this one point. So I could just bring it all here and define that, put a better node here, so it's a little more round, I guess. So then over here, I have one collective ground node, right? This is where I would all attach everything to my ground or my negative side terminal of my power supply, let's say, or current meter, my current source. And this is how I imagine it, and at least when I'm thinking about this problem, this is how I perceive it. So I can see the 3 nodes really straightforward and a lot easier. And this version of this visual of the problem will certainly help you later on when we start looking at more advanced problems. Okay, let me not think of things so rigid all the time. Let me think about it as a little more flexible. And if I had to physically design this or build this circuit, this is probably more in line to how I would do it on a breadboard. Okay, so hopefully that helps. So back to the problem again. So based on the circuit, hopefully you get the idea from the previous problem. That means by default, I1, right, it's going to be 6 amps, it's positive 6 amps. And I3 is going to be positive 8 amps. So there it is. It's just, so now if you think about it, there's 3 mesh loops, right? I1, I2, and I3. So I don't have to write too many equations. I only have to write one equation that satisfies that center loop. So I already know the far left, I know the far right. So the only thing I need to figure out is what's going on over here in the middle. And technically, that's what a supermesh is, but I'll go into more detail of that in the next problem. So what we're going to do is that for loop number 2, we're going to write the KVL equation for it to satisfy that. Let me just, again, copy and paste this image to make it a little more helpful, I hope. So let me copy that and move it as I go along here. I'm going to write KVL. Oh, great, I already did that. So with the KVL, I'm going to write one equation. Again, technically this is called the supermesh equation. Why again? Because we are not taking into account the current sources, right? And we're going to attack the problem, but I'll give you steps in a moment. So the KVL equation for the center loop is going to be, because I'll start here in this corner, and I'm going to go around clockwise. So I'm in loop 2, so then therefore there's going to be I2. I'm subtracting from I1 because it appears that I2 is opposing I1, and I'm in loop 2. I get to the 6 ohm resistor. 6 ohm is not being shared about anything, so just 6 times by I2. So resistor times by current gives you back a voltage. Resistor times by current gives back a voltage. Like I'm still in loop 2, so I'm 8 ohms. So because I'm in loop 2, it's I2, and then I'm subtracting. It appears that I3 is going opposing me. So it's 8 times by I2 minus I3. And that's it. As wild as that might seem, that's like 90% of the problem, right? Why again? Because we already know that I1 and I3, I1 is 6 amps and I3 is 8 amps. So I put those values in there. I only hopefully will have one unknown, which is my value of I2, and I can solve for that. Okay, so with some quick reduction, so you can pause it here if you like to see how I actually went through it, or you can try it out yourself. I distributed out the resistor value. I simplified this circuit. And when I simplified it, right, so, and again, I'm left with this easier version of the equation. I already know 2 of those currents, the 6 amps and the 8 amps for I1 and I3. And then I substitute those values back into this, right, and here. So I substitute back in the 8 amps and the 6 amps. And now I only have one unknown. That's it, which is my I2 value. Once you have the I2 value, hopefully, it's just plug and play, right? With a little bit of algebra, we'll get back I2 to be 4.75 amps, right? So hopefully that wasn't so bad. That it's not as bad as it seems, and because again, some of the information is already given to you. All right, I will go into a little bit more detail now, because now we're reaching the point which is hopefully a little more exciting and interesting to you. So we're now at the point where we have our 3 mesh equations, but we're at the unique one now, right? So there's this mesh analysis is using an approach here where before you can clearly see that the current source was isolated. It was, for example, it was on this side. But now the current, this 5 amps, is hanging right here in the center. So how do we define it, right? It's not really I1. It's not really I2, or it's not really I3. It's contributing to, we'll hopefully we'll find out what it's contributing to in a moment. So let's think about what is this 5 amps contributing to. If you want, you can pause it there and then write down this example. You can try it out yourself. But so how do we do that? And if you're struggling to visualize this, we'll temporarily move this 5 amps, right? And put in a resistor for a brief moment. And you'll remind yourself that, aha, so if it was a resistor, that if I call this one I1, I call this I3, that resistor has contributions from both I1 and I3, as I went over in a prior video. So how do we handle this? Very special case. So when this situation happens, step 1 is you remove the current source, okay? And you redraw, okay? So that's why right there I did it. I removed it, and then I also want to label my loops. You know, it might make more sense actually to label loops first. You can see it a little bit more clearly. So let me go ahead and label it so it makes it a little bit more easier to explain this later. So I'm going to call this loop here I1. I'll call this loop here I2. And I call this loop here I3. Doesn't really matter which one is which, by the way. It all should still work itself out. So now that I have I1, I2, and I3, and I remove the current, I'm going to have something that visually looks like this. Okay, so again, why removing the current? Because this is a technique to solve for when you have a current source inside of a 3-loop mesh equation. And then hopefully it'll be clear as I go through this why this is so significant on this particular technique. And I'll show you in detail. So this here, once I remove it, what I'm essentially left with is just 2 loops, right? So I have my loop here, which is the I2 loop. And then I have this giant loop here, right? Which takes into account I1 and I3. And that special loop in red is what is called our super mesh. Okay, so that's that one unique piece of our circuit, which I now combined. I moved the current source, and I'm writing an equation that solves for KVL for one giant loop, right? And that's what's so super or special about it. And it's given a name, our super mesh. Say it one more time. I remove the current source from my circuit, and when I remove the current source, I'm left with just two loops. One large one in red called a super mesh, and the other one just our traditional mesh current I2. So how does this technique work out? Well, we're going to write our super mesh equation, and we're going to write, so we're going to have 2 loops now. So we're going to have 2 equations. One's going to be our super mesh equation, and the other one's going to be our classic mesh loop equation. So let's try that out. So how does this work? We're going to do what we always do, right? We're going to go clockwise 99% of the time. And when I do that, I can readily call positive when I enter into a terminal for our components like our resistors. Enter into this resistor, calling it positive. I cannot change this. Whatever it says for the voltage sources, you read it. I'm entering to the positive voltage, so I'm positive 50. I'm entering to the positive 4 ohms, entering to the positive 6, entering to the minus 100 volts. Okay, so when I do that, let me try to copy and paste this as well in case I need to look at this in a brief second. So when we do that, let me shrink this down a little bit. Try one more time. So when we do that, we're going to have here one equation, right? So I'll do it with you. So we have I'm going to always start right underneath the voltage source. Usually my far left is easier for me to remember, so I always have a pattern. I'm entering into the minus 100 volts, so I put minus 100 because I am still in loop 1 territory, right? Remember, see these little dashes? This is part of the original I1 loop. It's going to be 3 times by I1 minus I2 because I2 is opposing the direction of I1's flow, right? Then in my super mesh, then I go into the I3 zone, right? So see that little divider? But I'm still 1 loop, so I have to still keep them quasi-separate. It's going to be 2 times by I3, and I'm opposing I2's direction. This is going clockwise. This is also going clockwise, but they're opposing each other. It's going to be 2 I3 minus I2. Then I'm entering the positive terminal of the 50 volt source. So plus 50 volts. Then I go into the positive 4 times it by, I'm still in the I3 zone territory, right? 4 times it by I3 plus 6 times it by I1, all equals 0. See, these are all voltage sources. So take a moment to take a look at that. And again, we'll practice this problem, a similar problem in a few minutes so you can get a sense for how this all works. So what we're seeing again is I wrote one equation that's called our super mesh equation. So we're not done quite yet. So we have one more loop. So I have to write that equation for that loop as well. So when we do that, and by the way, SM stands for super mesh. Before we go too far, I'm going to simplify this equation. I'm going to simplify this entire thing, right? So here's a simplification of what I've done here. So to save some time, I distributed to 3, distributed to 2, right? So put all my like terms together, all my I1 terms together, all of my I2 terms together. So I simplified my super mesh. I'm going to call that again SM for super mesh. I simplified it, and I have one super mesh equation, which I call it there. Okay. So take a look at that, or take a screen grab of that, and you should hopefully have this information in front of you. So once I have my master super mesh equation, I have one more loop equation to write, right? And that is the top loop. So here's the top loop again. The top loop is over here, which defines the I2 mesh current that I defined. I'm going to start at this corner. I like to start at the bottom left corner of all of my loops. And I like to go around. And again, as I mentioned before, so make sure I put the sign here. So positive, negative, because I'm going clockwise, I'm going to have a voltage drop. So I'm always going to be entering the positive end of my resistors. So as this is read, this is going to be read as 10 times by, I'm in loop number 2, so it's I2. Then then I keep going clockwise, and I reach here. So remember, on this side, it's going to be positive, negative, how we interpret this loop. So when we get over here, I'm going to have positive 2 time, and I'm in loop 2, so I'm going to be 2 I2 minus I3. So I'm opposing the I3's direction. Okay, then I get back to my final component, which is 3 ohm resistor. So it's positive 3 times it by, I'm in loop 2, and I'm subtracting it from I1 because I'm going across I1 zone. So this is it. This is my second equation. Again, I started here, went clockwise, entered all the positive terminals on I2's clockwise notation. So I gave it polarity as I went through it. And I have an equation that satisfies that second loop, which is really impactful. All right. So again, simplification. So we're going to simplify this, and to save time, I simplified it for you. So you can go ahead and either pause it or try this yourself. So I distribute this entire thing out. I distribute out my resistors, and I simplified all the same like terms, and I'm left with a secondary equation. So here's my second equation here. Okay. So go ahead and pause it if you need. So finally, once we have those two equations, right? So here's what we're left with our simplified problem. We're going to have our equation 1, which is our supermesh equation, and equation 2, which is our loop number 2 equation. And I have two equations, and as you can tell, 3 unknowns. I have an unknown of I1, I2, and I3, right? In both terms, I1, I2, and I3. So 2 equations and 3 unknowns. So how do we solve that, right? Is the challenge. And hopefully we can use some techniques that we've learned from our algebra class or pre-calc type classes to get ourselves ready for that. But ultimately, we should have to solve that. Well, sort of. So mathematically, if we try to solve it the way it is, we're going to still be stuck somewhere. So let me explain to you why. So the reason why is that we have to take into account a constraint. And what constraint do we have in our problem? Well, the constraint that we have is actually the current source that we originally had. So for our next step with our supermesh, we take out the supermesh, right? And then we develop the supermesh equation. So now we have to put our current source back in, or at least try to understand how this current is behaving, because our current source is part of our actual constraint for this particular problem. So let's look at it in very fine detail. So what is the relationship with this current source? Well, the current source, I'm putting everything in yellow. The current is going up into this node, right? And the only other branches that are attached to this node are affected by the 3 ohms and the 2 ohm resistor, okay? So that's how the 5 amps contribution to this entire problem is. So when I put it back in, I can identify that. Once I identify that, right, I can now look at, let me just copy and paste this picture to make it, again, a little bit easier for us. We don't have to keep scrolling back and forth. Just go ahead and copy. Let's paste it over here for you. Okay, so now when I look at this problem, I'm drawing it a little bit simpler with this variation, right? I'm just showing you what the node looks like, okay? And how do I know the direction of I1? Well, I define I1, it's always going clockwise. So if it goes clockwise, it's going towards the right, right? And it's entering this node. Well, how do I know the direction of I3? Well, again, I define I3 to be going clockwise. By the way, if I solve for I3 and it ends up being negative, this means it's going counterclockwise, so it's no biggie. So again, because I'm defining it to go clockwise, it is now leaving this node. How do I know the direction of the 5 amps? Well, they told me, they put an arrow on it, and it says that it's going up. So for my previous videos, I try to show you an explanation, which essentially says the sums of the ins will equal to the sums of the outs for all of our nodes. So In other words, if the currents that I have entering are I1 and I2 and the 5 amps, right? So here, I1 plus the 5 amps. And what current I have leaving this node is only the I3, right? So there's my sums of my ins and outs. And I like this variation because the sums of ins and outs is technically it's KCL, which means if I solve this equation over here and I try to solve it to 0, which means I either move the I3 to the left side of the equation, I'll leave it for 0 here, or if I move I1 and 5 amps to the right, I get back its KCL, its classic form. So either or of these are fine, or all three of these are all exactly the same mathematically. It's really, really important, especially later when we get to more challenging problems. Keep that in the back of your mind that you have the strategy on how to figure these things out. So why is that so important? We have our two equations, we have our two unknowns, right? And now we have to attempt to use some mathematical techniques to solve for it. One mathematical technique that we can do, we can take our equation of our supermesh and our equation number 2, and we can simply combine them, right? Or simplify it. And what we're trying to do mathematically is that we're hoping that we can somehow quantitatively remove either an I1 term or an I2 term or an I3 term. And right off the bat, you can see that I can't do that directly. So if I combine these two equations, 9i1 minus 5i2 plus 6i3, from this bottom equation, which is our equation 2, and we're left with 6i1, right, 10i2, and 4i3, and positive 50, which means I'm still not getting anywhere. Nothing actually simplified. I'm trying to simplify this form. So again, this is a strategy when you have two equations, and there should be 3 unknowns. We'll fix that for you. If you have 3 unknowns, right? So the strategy is that we're trying to simplify it. So how can we simplify that? Well, if I multiply the second equation, our second loop equation by 3, right? Both sides of the equation by 3, I get back 9i1, right? So I distribute this out. I get back minus 9i1, positive 45i2, and I distribute it here. I get back minus 6i3. And of course, 3 times 0 is 0. So I get that back. And again, why am I doing this? Because mathematically, something really cool happens, right? So when I combine that, this term here, 9, so 9 plus negative 9i1 gives me back 0. Extremely important. So I get back 0. Minus 5i2 plus 45i2 gives me back 40i2. The 6i3, okay, and the minus 6i3 cancel out as well. So I simplified it, and I'm left with an equation that's hopefully nice and easy for us. In other words, I get back 40i2 equals to 50 volts. So now I know for certainty that my value of I2 is going to be 1.25 amps. Isn't that pretty neat that we can do that? And we can actually solve for that by simplifying this, by using this method of trying to cancel out either an I1, I2, or I3 terms. Thankfully, mathematically, this worked out pretty nice and neat that we could actually use this to solve for I2. Don't worry, the next problem gets a little bit harder. We'll try that one as well to see what actually happens. Okay, and again, we can try all different types of things as well. What if I multiplied the supermesh equation by 3 as well? Then I'll be left with the following. I'll be left with 3 times 9 gives me back to 27, 3 times 5 gives me back to minus 15, 3 times 6 back to 18. And I'll see as well that the minus 15 I2 and the positive 15 I2 will cancel. So I'm left with this form, right? 24 I1 plus 16 I3 equals to 150 volts is what I'm left with when I distribute it out. And don't forget, most people sometimes forget, also multiply the right-hand side, so that 3 by the 50 gives me back to 150 volts, which is important to us as well. Okay, so interesting. But remember what we said before is that I1, right, and I3, we have 2 unknowns and 1 equation. So because of that, so we have here, we simplified it. We have, instead of having 2 equations and 3 unknowns, now we have 1 equation and 2 unknowns. We're still stuck, maybe, right? Remember, what's really important here is that we also said that we understand how this node behaves. We understand that the total ins will equal to total outs. So in other words, I know that I1 and I3 are related to each other in this form. Okay? This is extremely powerful. So because I understand that, I can now substitute into I1 or I3 this. I can either solve for I1 here, right? I can solve for I1 or I3. So if I left it as I3, right? So I3 equals to I1 plus 5 amps. I can plug in I1 plus 5 amps in wherever I see an I3, which is here. So here it is. So if I solve for I1, I'm going to have 24 times by I1 plus 16 times by I1 plus 5 amps equals to 150 volts. Why again? Because my goal is to get one unknown. This is going to leave me with one unknown. That one unknown left is going to be I1. So when I simplify that out, I get back the following equations, right? You can go ahead and pause it, but ultimately you're left with I1 to be a value. The value of I1 is going to be 1.75 amps, which is pretty neat. All right, so hopefully this is starting to click a little bit. And if it's not, don't worry. The next problem, it will be our final attempt of getting this. I think we'll feel better as well. And finally, I3, well, we could either keep plugging back into the original equation or just remember what happened over here. We can see that from our KCL, that node, that I1 plus 5 amps minus I3 must equal to 0. So if I know my value of I1 is the 1.75, and I know that I have the 5 amps over here, right, which is, or the minus, let's use this version here, I guess, the minus 5 amps and the minus 1.75, I can get back I3 equals to 6.75. So now we finally solved for I1, I2, and I3, which is really cool. All right, so now the last problem, we're going to do it again, and this time hopefully a little bit slower. And this is going to hopefully bring everything back together. So here's this variation of the example problem. So we'll go ahead and take a quick screen grab. So you can see now that this 2 amps, it's over here, but it's going to have a contribution from the current source here, I1, and the current source here, I2, right? But how, right? And how? And to quickly assess it in your mind, you could always replace that current source, at least in your mind, as a resistor temporarily. And you'll say, wait a minute, if it was a resistor, then it's going to definitely have a contribution between both loops. But how is that actually happening? And the strategy is to think about which node is actually being affected for a problem like this. Okay, so this is the tough challenge. So I'm going to show you, and then after that, you're going to be mastering this stuff. So what are we going to do again? We're going to define each one of our loops, I1, I2, and I3. Calling I1 here, 2, and 3, in case you don't see that, because it's a little bit light. Once I do that, I'm going to remove the current source, right? Remember that's step 2 for our strategy for Supermesh. And once I remove it, I'm going to have just one giant loop here, which is called our Supermesh, right? And I'm going to have a secondary loop over here. So I'm going to have 2 loops, okay? Again, I'm going to define everything as going clockwise. I love to start at the bottom left-hand corner and read it as I go around. And I return back to the terminal and as I complete, because I know it all nets to be 0. And I write down my Supermesh equation. So let's practice that with the Supermesh equation. Let me shrink this as well so you have a visual of this and put it next to everything so you can see it nice and clear. So here it is, and I'm going to shrink. So when we do this and I go around this clockwise, again, I like to start right underneath the voltage source or the far left corner, because I like to remember where I start always. Entering to the negative terminal, I read this always. If I go into clockwise for everything, then it's going to be positive, negative, positive, negative, positive, negative. Okay, so I'm going to read this as being positive 2 ohms times by, well, I'm in the I2 section of my loop, right, that zone, and it's not being shared. There's no other loop over here above it. So as I go to next 2 ohm resistor, I'm entering the positive terminal again. So because I'm in loop 2. Loop 2 is opposing. I didn't give this one a name. This one should be I3, right? So I'm opposing I3, so it's going to therefore be I2 minus I3, okay? So now I continue along this path, and I'm over here now. I'm entering this other 2 ohm resistor, so I'm entering a positive. Now I'm the I1 zone. So I1 countering the I3 direction, right? So I1 minus I3, all of it equals to 0. So there's my supermesh equation, okay? So again, see how I did that. Now we have to simplify that as we did earlier. We're going to just distribute out, simplify, put all our like terms together. So I saved you some time. You can see how I did this and how I simplified everything out. And I have a nice, hopefully concise, tight problem here in that this equation here. And that equation here is my supermesh simplified equation. Okay. And then I have one more loop left to analyze. And that other loop, so we put the arrow in there to make sure it's all in here. So here, let's do it together. So here's my other loop. So this loop here is called I3. And I'm going to start here. Then we're going to go here. Then we're going to go here. And then back here again. So if I start from this corner, so I'm going to put here start. Right? If I start there, how this is being read, this is going to always be, because I'm going clockwise, right? It's going to be positive, negative, and I can't add a positive, negative here. I read whatever I see. So I mean minus 6 volts, and over here, this is a passive device, positive, negative again. So when I do that, because I am now in loop 3, and I'm here, so I'm going to be 2 ohms times it by I3, because I'm in loop 3. I'm going to be subtracting it from I1. Okay, and then because I'm still in loop 2, loop 3, it's gonna be I3 minus zone I2 of the mesh, and then I'm going to entering into the minus 6 volt sign, so minus 6 volts, right? And then finally it would be plus 1 times it by I3, because the 1 ohm resistor is not being shared among any other meshes, so strictly just going to be the 1 times it by I3, and there it is. I have my second equation. I'm pretty close now to being done. I distribute what we have out. So I'm going to distribute this. You can see this as well. Here how it looks like if we distribute out. But more importantly, we're going to end up with this simplified variation of the problem. Okay. And then you have 2 equations, a supermesh equation and our equation number 2. And we have the same issue we had earlier. We're going to have 2 equations and we're going to have 3 unknowns that are available. And now that we do that, we either panic or we go back to what we learned a moment ago, right? It's not to panic, it's to try to think about which node is critical to it. And realistically, what I like to call that again is what is our constraints, right? And what is the portion of the circuit that we have to tackle that makes the most amount of sense? So here it is, right? We're gonna our big concerns. We put that current source back into the circuit. Once the current source is back into the circuit, I can do a couple things like I did earlier. I can try to simplify those 2 equations, right? By trying to find the like terms that are together. But if I look at that, sorry, I'm scrolling again. Sorry, I don't mean to scroll too fast. But here it is. So take a look at this. We got lucky over here. I have a 2i1 on this one. I have a minus 2i1 here. So those, if I combine these 2 equations, simplify out, which is exciting and helpful. So that's how this ended up being. So this 2i1 and minus 2i1 disappears. So it becomes 0. 4i2 positive and minus 2i2 gives it back a positive 2i2 minus 4i3 and positive 5i3 gives me back a 1i3. So I get back a nice simplified problem, as you see here, right, by summing these equations, which is really important. So now instead of having 2 equations and 3 unknowns, I have 1 equation and 2 unknowns. Okay, and now we can try other options to see, okay, what else could I fool around with this? I can certainly multiply one of them by 2. If I did that, then I could presumably simplify it. So I have, for example, an equation that satisfies a minus 2i1 plus this 6i3 equals to 22 volts. And now I have an equation that has I1, right? I'm just moving this around, so I'm trying to isolate the I1 by itself. And I could try to simplify this as best as possible, okay? So that's the name of the game when you're trying to tackle this. Okay, so now that we have some couple of strategies. Okay, so I believe I made a typo here, so please add this to your notes here, but this should actually be, I lost a -2, so over here, right? When I transcribed it, missing a value here, so this should be the -2, right? I1 should be there. So we have that as well. So now I tried to put the equation to multiple forms. What did I try to do again? Is I tried to find the way, if I can get lucky, and try to reduce it like we did from the previous problem and just get back a value of I1, I2, or I3 outright. But we could not, right? We couldn't just get that outright. We still ended up with two new equations with two unknowns, which means we're going to go back to our constraint. So we now have to look at the sums of all the ins and the sums of all the outs. But for where? So let me just copy and paste something for you so I can put it right next to each other. So let me scroll up for one brief moment, copy this here. And I'm going to now include it over here so you can see what I'm talking about, a little more clarity. So here it is. So we look at this problem here, right? And we look at the 2 amps. Our only thought process should be either we're going to try to evaluate this node or we're going to try to isolate this node. And the rationale should hopefully be logical. Well, I can't do this one because the 2 amps doesn't affect it over here because there's a voltage drop here. So this node doesn't make any sense. The 2 amps can't be over here either. This node doesn't make sense about it right off the bat because again, the 2 amps is not directly entering into it. There's a voltage drop that's going to happen here, and there's also clearly a voltage drop here. So I can only analyze either this portion of the 2 amps, this node here, or this side. Okay. If I decided to use this node, you would imagine that this 2 ohms is going to have 2 contributions from I1 and I3. So it makes it a little bit math heavy and makes us go literally in circles. So if we look at this particular node, it's really powerful. Why is that node so powerful? Well, it goes back to what we originally talked about. The first one is that we are defining everything to go clockwise. So when I define everything to go clockwise, I1 will be entering into that node. And if I defined I2 to also be clockwise, like I always do, right? It's going to appear that I2 is leaving this node and going up. And which direction is the 2 amps going? Well, thankfully there's an arrow on it. It says going to the right. So I can quickly write the KCL equation for that node. It's very important if you notice what I just did there. In other words, I can do all the sums of the ins will equals to all the sums of the outs. So I will get back I1 is the current entering, the 2 amps, and the I2 are only the sums of them are the currents that are leaving. So there's my KCL for that. So I could also write it in this form, as you probably recognize. I could also write it as I1 minus 2 amps minus I2 equals 0. That satisfies KCL. Or I can do minus I1 plus 2 amps plus I2 equals 0. And I also wrote down their KCL equations for this node as well. So now that we have that, we have these simplified equations that I showed you before, right? And how did I get this equation? This minus 2I1 is from earlier. I tried to simplify these 2 equations to 2 unknowns by reducing one of these unknowns. So I have a simplified equation, minus 2I1 plus 6I3 equals to 22 volts. And I did that for the other one as well, right? Because a 9 dropped out, and I'm left with this one as well. So now, when I combine my constraint, which is, for example, I1, this is my new constraint equation, which comes from the KCL equations, right? I can finally plug and play. So wherever I have an I1, I'm going to now put in my constraint of the KCL for that node, which thankfully takes into account this 2 amps, right? And I can simplify that because now I'm going to have 2 amps plus I2, distribute the ohms, so this creates an ohms times by current gives me back a voltage, right? And now when I do that, I'm going to have a new form of my equation. I have 2i2 equals to 6i3 minus 4b minus 22 volts. Reduce it some more, and I'm finally left with a new variation of my problem, which is I2 equals to 3i3 minus 13 volts. Okay, and I can repeat this again. So now notice I had those two equations. I simplified one of the equations with my constraint, and I put in my equation for I2, right, back into the top equation over here, right? And I am now left with this form, right? So I'm just going to distribute this out. Y from over here. And when you do that, I finally have my one unknown, right? So finally, so I can see I get back 7i3 equals to 42 volts. And then eventually I3 equals to 6 amps. So look at that very carefully on how I did that. And I'll scroll back up if I went too quickly, or just pause and go back. Again, this is for solving the problem of two equations and three unknowns. If this was three equations and three unknowns, then I could simply use a matrix and solve, or quick a substitution routes is not so bad. But in this form, the two equations and three unknowns, I have to use the combination of our constraints and these problems to solve. Okay. All right. So now that we have the 6 amps, we can now hopefully solve for I1, our other two variables, right? We go back to one of our prior equations, right? And here's we solved for I3. So now if I plug in my value of 6 amps to this problem, I'm left with one unknown, which is I1, okay? So if I do that, I get back I1 equals to 7 amps, okay? And then finally, because of my constraint equation, I1 equals to 2 amps plus I2, right? I can now solve for I2, will give me back 5 amps. All right. So if you made it this far, congrats. If you want a little bit more advanced understanding of what's going on, let's look at our solutions in detail. Well, we received I1 to be 7 amps positive, which means it's going clockwise. We had 5 amps positive, which is going clockwise. Does this satisfy KCL at this particular node? Well, we have 7 amps going in, 5 amps. So 5 and 5 are leaving. 5 and 2 amps are leaving. So yes, we have a net of 0 at this node. So it actually satisfies KCL. So it's really critical to look at that particular node. And this is how it looks like when you analyze it, just from understanding KCL, or Kirchoff's current law, at that particular node. So if I wanted to now, right, I can analyze everything just to be sure. So remember, because we solved for I2 is the same here as it left. So it's the same, current's the same through the entire branch. That means it also must be 5 amps entering to this node, which I'm going to call node C. We solved for the current through this loop, right? This loop I called it I3, and that current was 6 amps. So if I have 5 amps entering this node, 6 amps leaving this node, right? Then how much current is going across this particular 2 ohm resistor? Well, it has to still net 0. So in other words, I have 5 amps coming in, then I must also have 1 amp entering this node to have a net equals to 0, which is what KCL, Kirchoff, is trying to explain to us, is that they equals to 0, and that's another check. So now I can see that I expect to have 1 amp going across that 2 ohm resistor, right? 5 amps coming down, and 6 amps going down from there, which is pretty cool. And if I want to analyze node D, which I'm temporarily calling it node D, it's not really anywhere, but node D, I know with certainty that the 2 amps is going into it. I know the 1 amp has to be going to the right, because that's what I just solved for prior. So then how much current is going across this 2 ohm resistor, right? And what we're going to see is that it also must satisfy KCL as well. So it has to be 1 amp leaving or going downwards across that resistor. So I'm expecting 2 amps entering, 1 amp leaving, another 1 amp leaving, to net equals to 0, which is kind of interesting as well. Okay, and so that's, and then the final node, which is the ground node, if I know that I have the 6 amps throughout this entire branch, which means it starts here, goes here, it still stays 6, still stays 6. I have 6 going clockwise, positive 6. I know I have the 1 amp going down. Well, what's left? I get back the 7 amps, right? And it does get back me to Kirchoff's current law, that I get back the 7 amps that I originally solved for this particular problem. So everything checked out. So that's how it goes. This is how wild these problems could possibly get. If you made it through all of this, congrats. Hopefully you feel like you can master this now. It certainly takes at least 3 or 4 problems to get the full complete hang of it, but I believe with these 4 quick examples, you should be well within your way to mastering this. And until next time, thank you for joining the channel, and if you like what you learned, please subscribe.